So in this video here, let's talk about end behavior. So we've been looking at the graph for cubic functions and what end behavior talks about. So just drawing a quick sketch of the graph that we've been talking about. So cubic functions, we learned, kind of has this like S shape, or you can think of it as like a lightning bulb curve, lightning bolt curve, and has an inflection point that usually is in between the curve, the middle point of the curve. And you can see that one side is pointing up and one side is pointing down. And when we're talking about end behavior, we care about those two ends. So we can see that end behavior refers to typically the left side and the right side of the curve. And so when I'm talking specifically about an end behavior, let's write to the side here. If I were to ask you guys, what is the end behavior for this cubic function? Well, we can say that the right side, this right side here, is pointing up, or it's up. And then we can say that the left side here is pointing down based off the arrows. And so end behavior is just this simple idea, is like, which way is it pointing? On the left side, it's pointing down on the left side, and on the right side, it's pointing up. That's it. So whenever you're asked, what is the end behavior? Just look on the left side and the right side and tell me which way it's pointing. So for cubic graphs, usually one side is pointing down and one side's pointing up. But this is not the case for every graph. So like quadratics tend to either point both up or both down. So you can say that the left and right end behavior is either both pointing up or both pointing down. So that could be a combination. So let's get into other characteristics of polynomial functions. So if we kind of, turn the clock back a little bit, let's talk about linear functions. And we're going to apply a few vocabulary like degree of functions, if you remember what that means. We're going to look at the graph and we're going to label how many solutions they are, whether they are real solutions or maybe not real solutions. And we'll go into that. So let's talk first about degree of the function. When we're talking about the degree of the function, we're talking about the highest degree or the highest power on x. So in this first case here, we can see that this x is to the first power. So the degree of function has to just be 1, because in this case, the only power here is 1. Or the only x here is just x to the first power. And then this next one here, we can see this is to the second power. So the highest degree here is 2. So this is 2. Actually, let me zoom in. I don't know if you guys can even see the function. And this last one here, we can see it's x to the third power. And that's the only x here as well. So our degree of the function has to be 3. And so basically there was a mathematician that discovered that based off of the degree of the function, or the highest degree, that tells you how many solutions there are. So in this case, this first one here should have 1 solution, and this one here should have 2 solutions, and this one, this cubic function, should have 3 solutions. But what does it mean to be a solution? Well, it means how many times does it cross the x-axis. So when we're talking about solutions, we're actually looking at x-intercepts. So let me just show you what that means on a graph first. So let's just draw a graph here, a coordinate system. I'll just draw some coordinate system here. And if I were to graph y equals x to the first power, it's actually a very simple graph. It's basically a line. It's one of the most earliest graphs we've ever made. And so if you were to use a graphing calculator or just use a, make a chart and graph it, the points, you would get this line that kind of looks like a diagonal. And you'll notice that it hits the x-axis at one spot here. So if I were to look at the x-axis, this line crosses it 1 time, and that's why there's 1 solution. So when we're talking about solutions for a equation or a function, we're talking about how many x-intercepts are there, and there's just 1. Now, oftentimes solutions can be known as x-intercepts, zeros, or roots. They all mean really the same thing. They're just saying, what is the solution, or how many times does it cross the x-axis? And it only crosses it one time, so there's only one real solution. And it's real because I can see it. So there's one real solution. Now I want to explain why they're called zeros. And the reason why they're called zeros is because that's where where y equals 0. Sorry, that's where y equals 0 on the x-axis. So that's why they're also, x-intercepts are also called zeros. It's weird, but that's just vocabulary. Sometimes we also call them roots. So there's one real root here. There's one real zeros here, or one real x-intercept. It's all the different ways you can describe what a solution is. All right, let's talk about this one here. So you guys remember, anytime you have x squared, this is going to be drawing a parabola. And so if you were to use a graphing calculator, you might notice there's a -4 here. So it causes it to shift downwards 4 units. And so now it's sitting here for the vertex, and it's going to be, graphing upwards. Actually, let me do a blue line to be consistent. There we go. And so we have a parabola. And I want you to notice with this type of graph here, how many times does it cross the x-axis? Well, it hits it 2 times. And that makes sense because in this case, this is a quadratic. The highest power is 2, so there should be 2 solutions or 2 x-intercepts, and there are. So there are 2 real solutions here. All right, and our next one gets a bit goofy here. So we've learned how to graph cubic functions. This also has a -4, so it is going down. And you guys might have learned that you'll have to find the inflection point first. So you go down 4, plot your point. Let me just do it in blue. And then the slope here is technically a 1. And so you would go up 1 over 1, plot, probably somewhere in this realm, and you would go down 1 over 1 plot, and then you would curve up and down to make your graph. So I kind of did this pretty roughly, but I'm just trying to get a picture of where does this cubic function cross the x-axis. And then we notice something strange, or at least I notice something strange. So when I draw this cubic function, I only notice one x-intercept, and it hits it right here. This guy will never touch the x-axis because it's pointing downwards. It's never going to come close to the x-axis. So what the heck? I only have one solution here when there should be 3. What is going on? It doesn't follow the rules of principles that algebra should be. By determining the highest power, you should have that many solutions. So what's going on? Well, it turns out there's only one real solution here. But that doesn't mean there is only one solution. It just means that the other 2 that you don't see are imaginary solution. And today we're going to get into the nitty-gritty of what does it mean for an imaginary solution to be on a real graph. Well, turns out imaginary solutions on a real graph don't show up because they're imaginary. They're hidden from us. But the algebra, if we were to break this down to solve for it, we actually would get imaginary numbers. You just don't see it. And that is the cool part about mathematics. All right, so let's get into what we're going to be practicing in this video, which is talking about taking a graph, graphing it with using technology. We are going to be using Desmos today. Actually, let me write this out for you guys. You're going to be using Desmos. It is an online website where it actually is a graphing calculator. It's one of the highly recommended ones to use. So you will need your MacBook or like a computer to do this. You'll be typing these equations into Desmos, and I'll show you how to do it. I'll walk you through. But before I do, let's go ahead and find the degree of the function and leading coefficients. So here you're given a few polynomials. As you can see, there are many terms in these equations. We call that a polynomial, poly meaning many, nomial meaning terms, so many terms. And what we're going to be doing is finding the degree of the function, which just means the highest degree. Leading coefficient is the number in front of the highest degree. And we're going to also graph it. So we will need to do a rough sketch of each graph. So I'm just going to draw a chord plane to kind of show what that would look like later on. We're going to need to know how many real and imaginary solutions there are, and we're going to need to know the end behavior. So when we're talking about end behavior, we're talking about what's happening or which way is it pointing on the left side of the graph and the right side of the graph. And so in this case, you're going to tell me, which way it's pointing right, which way it's pointing left. And so I'm just going to label for us real quick what we're expecting to see. All right, so let's get started with figuring out the highest degree. So the highest degree of this first one here, we can kind of see is x to the third power. So we can kind of see that they're already placed in order for us, and they should. This is a very good practice, or kind of a good manner in mathematics, is to make your first term your highest power. So this is to the third power. So this tells me I should have 3 solutions. Now I don't know if those solutions are all real or there could be some imaginary. The next one here is to the 5th power. So I know I should have 5 solutions. The next highest power looks like is to the 6th. Oops, I meant to use a highlighter. And so this will be 6 solution. And my last one here also looks like is to the 6th power, is the highest power here. So that is also 6. So degree of the function just means I want the highest power out of the function. So my highest powers were these powers. The other ones were too small. All right, now let's take a look at the leading coefficient. So once you find the degree of the function, the leading coefficient is always going to be the term that is holding the highest power. So all of these were the highest powers. So now I just have to look at the number or the coefficient in front of that term. So the first one here is a 1 because this x does not have a number in front, so it has to be a 1. The next number is a 2 in front of the x. And this one here is like a negative 1. Since there's a negative in front, it has to be a negative 1. Tricky. On our 4th one here, it looks like it is a 4 in front of this x to the 6th power. So we have a 4 as our leading coefficients. And leading coefficient is usually helping you figure out whether your end behavior is going to be pointing up and down. So oftentimes if you have a negative in front of your leading coefficient, you might have a flipped graph. So it could be pointing down, or it could flip it being up again, but usually it's going to be pointing down if it's a negative. So in this case here, let's take a look at the graph next, because I won't be able to figure out how many solutions there are unless I know what the graph looks like. And so this is where we turn to Desmos here. I'm switching the camera over to Desmo. So give me a few seconds to get this set up here. All right, so what I'm going to be doing is popping this equation into, so part A's equation in here. And what you have to do is type it out using your keyboard. And I usually just start off with the y equals. So I'm taking the first equation and putting y equals. And now I need x to the 3rd power. And so I'm just going to find my x, which is here on the keyboard. You can also use this keyboard here to type in everything. And so if I wanted a power, I can just press maybe this button here, and then this is a 2, but I need a 3, so I'll just click on it using my mouse and just hit the delete and make it a 3. I want to also show you another way you can write exponents, but let's first put the x to the 3rd power. After that, I'm going to use my arrow key to come down, or you can just use your mouse here and just click on it so you can come down. Now I need minus 2x, so I'm going to hit minus on my keyboard right here next to the 0, 2x. But what I'm going to do to get the exponent to be there is instead of using this square, which is really easy to do, what you can do is hit Shift and then hit 6. You see this caret button right here, this like arrow button that's pointing up. We call that sometimes a caret button. You have to hit Shift to get it. And when you do in Desmos, it makes an exponent spot for you. And then I can put the 2, and then I'll just hit my arrow key or just hit the mouse to make it come down. And so now I have 2x squared. Now I need a minus x next, so I'll type that in. And then I need a plus 1, it looks like. So I'm gonna hit Shift, plus, and then put in the 1 that I'm looking for. And I should have a graph on this side. So you can see that it's graphing for me. Let me pop this keyboard down. And now I have a graph. I can zoom out in case like I want to get the full picture, but it looks like when I zoom out, the picture gets too compressed. So I'm going to zoom back in to kind of get a better picture of what I'm looking at. So what I like about Desmos is you can interact with it using the zoom in feature, and it's really easy to do. You can trace it so you can figure out where does it cross the x-axis. So I'm going to do a rough sketch of what this looks like. And when I do, I notice there is 1, 2, 3 solutions. So I'm going to pause the video right here. Kind of put this to the side and try to draw that graph, just a rough sketch of it, like I said. So let me grab my marker here. Let's do this in blue. So it kind of looks like goes down, then back, down here, and then up. So it like goes up, down, back up. And so it crosses at 2 significant places. Actually, it's more to the side. It's not actually at the origins. Let me fix that because it's going to bug me. So it's like goes up, and kind of like that. Yeah. Sorry, mine was a little bit too close to the origin. So I have 3 real solutions here. So I'll just write 3R or 3 real solutions, which is great because there are 3 to begin with. So there are just 3 real and no imaginary. So you could write 0 imaginary or just not write any at all. Actually, I'm just going to let that go. That was kind of weird. All right, so that's how you type things into Desmos. And what I'm going to do is type these already in and then just show you the picture of what your graph should look like. So you will be responsible to type it into Desmos and see what they look like. So you can do that on your own and practice using Desmos. We'll be using Desmos for the project in this chapter. So for this chapter here, there are no tests. There is just a project. So be practicing your Desmos skills so that way you are ready for the project when I explain that later on. So here I need to start graphing. So if I plug this into Desmos, I get a graph that kind of looks very similar to the last graph. Kind of goes up, then it comes back down. That was kind of a weird curve, comes back down and then goes back up. So very similar to last time, and it hits it in 3 places. So there are 3 real solutions. But here's the thing, there should be 5. So the other 2 must have been imaginary. So what I'm doing here is just taking how many do I have real that I actually can see on the graph, subtracting that from the degree of the function, and that leaves with me 2 imaginary solutions. Oh, it looks like I forgot to fill in the end behavior. So let's just do that real quick. So the end behavior for this graph, if we looked on the left side, it's pointing down. On the right side here, it's pointing up. So, oh, I think I did that opposite. I always do that. I'll fix that real quick. So the right side is pointing up and the left side's pointing down. For this case here, the right side is pointing up, left side's also pointing down. All right, so moving on to part C here, I'm going to plug this into the equation. Make sure you put that negative in front of x when you plug it into the equation because that does change the game. So when I plug it in, I get a really interesting graph. It looks kind of like this when I plug it into the graph, almost like a parabola, but not quite. It kind of looked kind of wonky when I plugged it in. But what I saw was that it touched the x-axis at 2 points. And so in this case, there are 2 real solutions, but there really should be 6. So 2 subtracted from 6 is 4 imaginary solutions. And it looks like both the end behavior, so left and right, are pointing down. So I'll just write down for both of these. And our next one here is 4x to the 6th power. So if I plug this entire equation into Desmos, I get like this really strange looking graph. It kind of like goes down and then kind of like a wonky back up, but they're both pointing up. So my end behavior are both up. It looks like it crosses it at 2 points. So there are 2 real solutions, but there should have been 6. So there are still 4 imaginary solutions. And that's it. So that's how you find the degree of the function, the leading coefficient. You'll have to graph it using Desmos or some sort of graphing calculator. And then the degree of the function and the x-intercepts will help you locate how many real solutions there are and imaginary solution. And that's basically it. All right, in the next video, we'll analyze some more graphs. Bye, guys.